Today, it is my great pleasure to introduce Professor Ni from the University of California at San Diego. Professor Ni has his PhD from the University of California, Irvine. He didn't move very far, where he worked for Peter Lee. Did postdocs at Stanford and Purdue. Okay. Before going back to Southern California, where he is now chair of the department.
Unfortunately.
Well, whatever. In any case, thank you for taking the time from your busy administrative and research schedule to come and give us a talk on Plurisubharmonic functions and heat equations.
Thank you very much. That's my great pleasure. To give me these opportunities to taste the winter. Well, it's a spring, in fact, right? We don't really have a winter, really. So it's sometimes get a little bit boring. My talk is on Plurisubharmonic functions and heat equations. So I learned. Yeah, I didn't move very far, right? So probably I started to do optimal transport at that time. Anyway, so that's the outline. That's my plan. So the Plurisubharmonic functions mainly concerns the theorem I'm going to talk about is concerns so-called Liouville type theorems. So I'm going to tell you what is it and what kind of theorems we proved. And mainly the results are all proved with respect to certain curvature conditions. Right? So the whole geometry business is about to understand the subtleties of the curvature. This slide has been around for many, many years still. So nobody really completely understands all the issues about curvature. So once I had a conversation with Bert Cosden, he told me he was the advisor of Jim Simons, right? So he told me the curvature of tensor probably is the most mysterious tensors one have to deal with. So then I mentioned some applications of this Liouville theorems, so-called gap type theorems. I tell you why we started this and what's the relevance. And then I'm going to mention connections with a subject called solving Poincare long equations. So Poincare long equations is equation studied, of course, by these two guys. But it's overdetermined linear equation. So usually you cannot solve it, but for some cases you can. And if I can, I try to explain there's some technical issues involved in solving these equations and why a parabolic method can prevail. And that method particularly related to, in my point of view, it's an infinite dimensional analog of this echoticity theorems, in a sense, book about dynamic Hamiltonian systems. So, so the most recent result in these talks are mostly joined work with New. She's half of my student. I'm one of advisor, and also some of the work result are joined with Fang Yang. Okay, start slowly. So let me just try to put everything up first, then we talk about it. We start with the Liouville type of theorems, right? So the more well-known ones are on harmonic functions. So on Euclidean space, you can easily prove harmonic functions of sublinear growth is a constant. So namely, the function fx absolute value is smaller than is a little O of Rx, R being the distance. So the result can be also generalized to curved space, not flat space. But you need positivities. because you're on bonded disk, on unit disk with Poincaré matrix. So you have lots of bounded holomorphic functions times bounded harmonic functions. So you cannot expect such kind of result. The positivities, the first one was by Chen and Yao in 1970 something. So they prove such generalizations on curved space. So if you have a Riemannian manifold, whose rich curvature? Rich curvature is kind of like a trace of the curvature. So it's rich curvature is a tensor exactly the same as a metric. So it also arises in Einstein's equations, right? So it's not too strong, it's not too weak. So there's also a trace of the Ricci becomes scalar curvatures. That's not enough to prove the result. So that's what the generalization did by Chen and Yao. So really the development method called gradient estimating method. So the method, of course, was around as a PDE method for a while, but this guy is probably the first one adapted to the geometric settings to see the curvature relevance of this estimate. So, for this kind of Liouville type of theorems, you need harmonicity. Harmonicity is the equation, right? So when I teach courses, I always explain harmonicity as a combinator. Namely, you have mean value properties. So your value is always same as your neighbors. I mean, the average of your neighbors. So everybody's happy. The theorems I want to talk about mainly is for subharmonic functions. I mean, my title is Plurisubharmonic functions. It's kind of like generalizations of harmonic functions, subharmonic functions on complex planes. So subharmonicity is kind of a depressing condition, right? So because you're always smaller equal than your neighbors. So nobody is happy. You still can prove some theorems, right? So there's a theorems which I learned when I was in undergraduate student learning PDEs. So you can prove on complex planes. So a subharmonic function, which if it grows slower than log of the distance function, it must be a constant. So distance function, log of the distance function is like the, right? So it's a fundamental solution. So that's kind of like critical growth rate for subharmonic function. You can prove this by using comparison principles, whatever, with the fundamental solutions. So okay. So the main thesis of the proof can be formulated in terms of some connections between the Plurisubharmonicity, which is like a complex convexity. So so if you have a real valued function, you look at Hessians, right? So complex Hessian is kind of like average of the real Hessian. For instance, like Plurisubharmonicity is really just Laplace of the function's bigger connectivity. I mean, subharmonicity, right? So Plurisubharmonicity is kind of like a complex analog of convexity. And there's also the relation between holomorphicities, namely relation with holomorphic functions. Because holomorphic functions, if you take norm of holomorphic functions, or if you take log of the norm of holomorphic functions, it's always Plurisubharmonic. So there has certain convexity there. And then there's also positivities of the curvatures. Okay? They are related in a very interesting way. So here I want to say one result, which is kind of underlying the proof of this Liouville result for Plurisubharmonic functions. Okay? So this result is related to this monotonicity for harmonic functions discovered by Almgren, so-called frequency monotonicities. So I'm going to show you why, okay, in a minute. But first of all, this result also relates to this more classical result of Hardy and Poria-Ziegel. So they prove the average of holomorphic functions, LP norms, is a convex function of log R. Okay. So I mean, the three circle theorems is really for p equals to infinity. That's the maximum. That's Adamat's result. Right, there's a result I proved about holomorphic functions on Kähler manifolds with some non-negativity conditions on the curvatures. Okay, there's a curvature called a bisectional curvature. Formally, I mean, it's just the curvature tensor act on. So this is non-negative for any x and y belongs to the so this is for any point p. So what is it? I mean, this positivity is really how should I say that, right? So for instance, like a complex projective spaces, of course, has positive or non-negative holomorphic bisectional curvatures. So there's lots of metrics you could construct it also even on Euclidean space, right? With not flat metric, with non-negative.
What is Z?
Oh, I tell you in a minute. Okay, I just try to explain this curvature conditions first. So this curvature condition is a little bit, I mean, it's a well-known conditions about geometry is sectional curvature. So that's how Riemann starts with the Riemannian geometry, right? So sectional curvature is really just you take a plane, and then you look at the plane, how that you take a tangent plane, you look at the so-called exponential maps. Namely, you want to look at how the manifold looks like near in the neighborhood of the point, mimic in the very close approximation of that plane. So you look at that basically two-dimensional objects, and then you look at its Gauss curvature of that two-dimensional object. That is the Riemannian sectional curvature. So bisectional curvature is kind of like it's kind of like all the complex analysis, like hashing is average of the real hashing. You have to add 2. This sectional curvature is also it's average. You have to add 2 because x and y are complex vectors. So they generate complex planes. So which is 4-dimensional. You have to add in 2 real 2-dimensional sectional curvature. That's what the bisectional curvature is. So the result is conclude about some functionals convexity, okay, of a T. Okay, I show you what is Z. Thank you. So the Z. So the Z is really the average of the LP norms on the manifold with respect to the heat current. Okay, actually is the fundamental solutions. So you average that, the LP norms of the holomorphic functions in terms of the fundamental solutions. Okay, so the DP is essentially it's a derivative. Okay, so that's the average of the. I mean, if P equals to 2, that's exactly the average of the Dirichlet is the Dirichlet energy with the weight of the fundamental solution. Okay, so I is the quotient, essentially. The derivatives, quotients by itself. So that's why this is kind of like parabolic versions of Almgren's frequency. Because Almgren's frequency functional is the Dirichlet energy divided by the L2 energy of the harmonic function. So this is some parabolic analog. So the convexity of that is equivalent to the monotonicity of the quotient. I mean, you have to formulate in terms of log t, because there's a t in front of it. Okay, so that is that monotonicity is really the key of the result of Liouville theorems, why it holds on general manifolds. So now I explain that. At least that's the one I used when we proved it. Okay. So on Euclidean space, you know such a result holds because you could cut the Euclidean space by all the complex planes. If it's constant, it's constant. All the complex planes. So you use the result of the two-dimensional case. But on general space, you couldn't do that because you don't know. You could exhaust the whole spaces by just some special curves. You require some different method, right? So the theorem we proved is, that's what I proved with 10, is under this condition, bisectional coefficient and activity. You could prove it. So one proof of this result can be done using this principles I just illustrated, this convexity principles in terms of parabolic equations. You kind of like, the proof goes like, you try to make use of monotonicities. You deform the equation, you deform the function by Hit equations. You try to understand how the solution behaves as t goes to infinity. Okay. So here, I mean, this relation between this and the analogy between this and the Brookhoff's theorems comes in this way. So you try to use the spatial conditions of U to transform into estimates along the solutions of the Hit equation along the t. Okay. So then how the monotonicity is going to be used, right? So the monotonicity basically has a convexity there. So it's not just a monotonicity, it's it's convex in terms of log t. So the convexity, the sub growth in terms of log r transform into sub growth of log t. Okay, so that convexity forces you, the derivative of the functional has to be vanishes. So then you from there you infer the function you started with has to be harmonic. Then you're done with the business. That's how the proof was.
What is r?
R, the distance function. I'm sorry. Rx. It's always the distance with respect to some fixed point. A priori.
Oh, okay.
Fixed.
Good. Okay.
That's the distance. Okay, so that is the result. Okay, so the result recently has some development and got we work out some different cases. Okay, so this involves some subtleties about curvatures. Okay. So I'm just doing a quick review. What is a Keller manifold? Keller manifold just really means the metric, the so-called Hermitian metric on the complex manifold satisfies additional conditions. So formally it just says this differential form is declosed. But in reality, what really it means? It just means in the complex world where you do everything in terms of complex variables and the complex geometries, and in the real world, you do everything with respect to Riemannian geometries. You do Laplace of Beltrami operators, you do Hessians, etc. On the Keller world, these two matches. the complex language, complex techniques, complex conditions matches with the Riemannian ones. That's what it is. Okay, so I explained this bisectional curvature conditions. Okay, there's another curvature conditions. Bisectional curvature conditions was most studied because this is, at the earliest stage, there's some conjectures in terms of bisectional curvatures on the Kähler manifold has been settled. For instance, the most famous one is this Frankel conjecture. So namely, if you have a compact Kähler manifold with positive bisectional curvatures, then it has to be biholomorphic to complex projective space. This was proved by Mori in a little bit more general setting using algebraic geometric techniques because band and break. Right? So it has to deform holomorphic curves in p-adic numbers, then apply to complex cases. Then there's a complex geometric proof by Su and Yao afterwards. So, but still, there are open problems regarding to classify or understand the manifold with positive bisectional curvatures in non-complex setting. It's not completely solved. So it's still, people try to understand what's the complex geometric implications of this curvature. It's not completely clear yet. But those are early conditions. Then there's also a much weaker conditions called a holomorphic sectional curvature. Okay. So it's just, you insist this y has to be the same as x. That's what it is. There's much restrictive conditions. So this curvature recently has several works. I mean, used to be, I mean, has been around in geometry for a long time, particularly for complex geometry. But recently, there's several developments regarding the understanding of the manifold of this curvature. So, for instance, and this is a three development. One I'm going to mention is by Gan Liu. So he's really a functional theoretic. Zero manifold, bigger than zero or smaller than zero. He's really a functional theoretic understandings. There's a work by Wu and Yao on a manifold with compact manifold with negative compact. And also, more recently, there's another, sorry for confuse you, they're all Chinese names. So there's another guy made an advancement in understanding compact manifold with holomorphic sectional curvature positive. So Liu's result is really functional theoretic. He, first of all, generalized what we proved to this setting, and then he made some good use of it. He proved the ring of certain holomorphic function we call polynomial growth holomorphic functions, right? So the ring is finally generated. So it's kind of like a non-compact versions of the finite generation problems for the algebraic geometry about algebraic manifolds, about the rings generated by the sections of canonic line bundles. Okay, so the Wu and the Yao's result is to understand this kind of manifold, you flip the sign, but it's compact with the holomorphic sectional curvature negative. They prove such a manifold always admits a metric whose Ricci curvature is negative. So those kind of manifold is well understood from algebraic geometric point of view. So that's something they did very recently. And also there's another result. This is more recent. This is, in fact, this was a problem by Yao, right? So Yao had a conjectures saying compact manifold with holomorphic sectional curvature positive has to be algebraic. This guy is give a proof. So this curvature conditions comes more recently. So more, I mean, this curvature condition was around for a while, but the study becomes revived, become more active in recent years, like last couple of years. Okay. There's also another one. Okay. For complex manifolds, you have lots of games to play. This is called we call it orthogonal bisectional curvature. So you only insist on non-negativity when the two vectors are perpendicular to each other. Okay. So there's another one called a non-negative quadratic orthogonal. So it's formally it's very clear, right? So this condition implies this because this is arbitrarily two pairs. This is orthogonal two pairs. Okay. So formally also this implies this because this insists for unitary basis. So when you take unitary basis, I and j perpendicular, this is non-negative. You multiply some square of some real number, so it's always non-negative. So summation is non-negative. When they are same, you don't have anything contributed, so it's always okay. This is not just formally we're doing this, right? So this condition, in fact, was arised in 1960s in analysis, basically in the work of Bishop and Goldberg. They tried to prove some vanishing theorems about some one-one forms, right? So in their computations, this condition arises. So there's some funny curvature conditions arises in geometry coming from analysis, purely from analysis. For instance, there's another much well-known conditions called positive isotropic curvature. So there's some recent works by Shen and Prendel and others in understanding the manifold, the topology of such manifolds. So that condition completely coming from the analysis. It's from second variation formulas of the of harmonic maps. So it's not geometric conditions. It's coming from analysis, but turn out to be have geometric implications. Okay. That's another condition. So so first of all, Liu also generalized the previous theorems we proved to the cases with non-negative holomorphic sectional curvature. Okay. So
sorry, what year?
What's that?
What year? When?
Oh, when? I think he did it. This paper was probably 2015, or I'm not 100% sure. Probably it's around 15 to 16. It's right. I mean, it's already appeared. There's also examples showing this conditions is not just formally one is stronger than other. They are really, because you can construct various metrics with one conditions that's not with the other. Okay. So the last one I should mention this non-negative quadratic orthogonal bisectional curvatures. The classifications is completely, even for compact cases, it's not completely done. There's lots of more examples. So there's a whole homogeneous spaces examples. So we don't have really good understanding of it yet. So the first result I want to mention is this generalizations we did on our previous result, which is orthogonal to Liu's result. So our paper is not it's on archive, but it's not published yet. It's we prove this for the conditions under orthogonal bisectional curvature, and we have to also assume it's non-negative reaching. So the curvature operator is very, very strange in the Kähler case. For instance, you could come up with an example. Okay, so there are metric examples. Okay, metric examples showing various curvature conditions are really different. Okay, But the last example is really algebraic example. In the sense, I have a curvature tensor satisfies this properties, but I don't know whether or not it's curvature of a metric. Okay. So this one is counterintuitive. It says if x and y are perpendicular, they're non-negative. If I put all x here are non-negative, but I don't know this is non-negative. In fact, it's not true. This is an example. Because this is not quadratic forms. This is full tensors. Okay. You could have a situation like this. It's a bit of weird situations. And also, there are examples showing the conditions of Earth is perpendicular to holomorphic section and curvature being positive. Because you could have metrics with all conditions, but holomorphic section and curvatures can be negative. Okay. So
when you say Liouville theorem, you mean bounded function or
No.
with some exponential
sublog.
function?
Sublog R is a concept. So this condition of orthogonal non-negative orthogonal bisectional curvature is really a Kähler analog of PIC. PIC means positive isotropic curvature. Okay, wow. So mathematicians always use the wrong names, right? So when we see positivities, in many cases we really mean it's non-negativities. It's like positive currents. Really, it's non-negative currents. So the PIC is a condition, as I mentioned earlier. It's coming from this second evaluation for computations of harmonic maps. So it really means what? Means the curvature tensor restrict to a complex plane, which is totally isotropic, being positive, being non-negative. So this Kähler cases has an analog of that condition. So this is completely from algebraic point of view. If you look at it from representation point of view, you can formulate it very invariantly about the curvature conditions. So that's exactly the Kähler analog. Okay, so I guess I explained the second one. It's really orthogonal to holomorphic sectional curvatures. And also it's independent of Ricci. You could also have both conditions. You could have non-negative orthogonal bisectional curvature. Ricci curvature can be negative, and the Ricci curvature can be positive. So there's lots of rooms. So that all implies scalar curvature being non-negative. All these conditions, including holomorphic sectional curvature. Okay. So Canlew's proof is a very nice. So this somehow was missed by people. I mean, if people working on PDEs on complex analysis, I'm sure they're aware of this long ago. But it's just they probably didn't aware this is a condition. You can make it on a manifold associated with curvature conditions. So it's really it's just if you take a distance function on Euclidean space, let's just take it back. It doesn't really matter. Okay. So now you look at the hashing of it. This is on CM. So then it vanishes if X is so-called complex radial direction. So this is really just the regular rate. If you want to expand it, it's really just the real radial direction plus minus square root of -1 of J of it. This guy requires radial. It's E. J of it. So this is complex radial directions. If you put that, becomes 0. So the reason is kind of, you can compute it in your head, right? So when you look at the hashing of log of distance function, if you're in the real radial directions, without log, the hashing equals to 0. So if you put a log, you have to subtract. So there's some minus terms. And on all the sphere directions is all with eigenvalue positive. So there's two cancels each other exactly on this complex radial direction. Make it equal to 0. Then you could have a proof. Okay, I oversimplify things a little bit. So Galileo observed if you have holomorphic sectional curvature and non-negative conditions, the same result holds. You have to change this by general distance function. I used R. Okay, X, you have to change it by the gradient of R minus square root minus 1 of JR, gradient of R. So it's really the holomorphic. Intrinsically, you can define the holomorphic directions, radial directions. Okay. If you put that in, the result has to be changed into the equality changes to inequality. So then this simple maximum principal argument proves the result. But that proof, nevertheless, does not really, we don't know how to make it work for this different conditions, which is perpendicular to that. As I explained, if you look at this case, if you look at the perpendicular ones, the eigenvalue are all positive. Okay. If you prove such kind of functions has a upper bound which is positive, it's kind of useless. You cannot apply maximum principles to do anything. So you need a very different method. So maybe I skip the proof on that. But there's a related topics, we call it gap theorems, right? So this is motivated by relativity to some degree. Okay. So what exactly the gap theorems tells you? Okay. In relativity, there's a theorem called a positive mass theorem, right? So it basically tells you the mass should be non-negative if you are not leaving a vacant. So, but it takes lots of effort to prove it. Okay, so what exactly the mass is, that's also a question, right? So different people have different way to define it. So there's one way to define it using average of the scalar curvature at infinity. So that's the so-called ADM mass. Essentially, you just take the scalar curvatures expressions and do integration by parts, become a flux integral from the spheres. It's just the integrations of the scalar curvature over balls, and they look at the limit at the infinity. So that's one way to formulate the mass. And there are some results in these directions. I mean, originated by Su and Yao in 70s. And they look at the cases of non-positive cases, okay? Not non-negative. They have to flip the sign of the curvature. Then they also did something for the non-negative cases. This was done by 3 of them. So Mock joined the force. 3 of them wrote a paper and proved similar result for the flip cases. So essentially, they try to make it as an understanding of the manifold, what positivity really means, so at infinity. So there's a result I proved several years back for non-negative bisectional curvatures. So this result basically is saying if the average of scalar curvature at infinity is a little O of R minus 2, namely decays faster than the quadratic, then the whole space has to be vacant. Basically, you can prove the manifold is flat. There's no curvature. If you at infinity, there's not enough mass, there's no mass. That's what the result says. So there's a lot of work in these directions. Starting with even I mean after Mok Su Yao's result. I mean Mok Su Yao proved result under much more conditions. They're throwing lots of conditions into this problem, and there's some work along this line uses heavy machine of the Keller-Rich flow. I don't understand. So there's a work of Chen and Zhu. There's also other people, like Xi also has some work in that. This is a student of Yao in the 90s. Okay, so this can also be pushed further. This is a new result I'm going to mention, is you can prove this under this orthogonal conditions. You don't really need the full bisectional curvature. You only need the orthogonal bisectional curvature.
What do you call it, the gap theorem?
Why you call it a gap theorem?
Yeah.
It really gives you a gap in terms of the decays at infinity. It just means at infinity you cannot decay too fast. Anything faster than quadratic, it has to drop to 0. What do you propose to call it?
Well, I think eigenvalues from gaps and so on.
Oh, okay, right. This is completely different from eigenvalues of the gap theorems. This is really, this is, as I said, this is really in line of the positive mass. So it's really like what the positivity means at infinity for a manifold. Okay. So to prove this, we have to solve this Pongarello-Long equations. Okay. So I explained to you what is the equation, and then you can see why this result follows from the previous result of Liouville theorems. So it's kind of like the Liouville theorems has some nice applications. That's the application. So the functional theoretical result sometimes can be used to prove geometric statement. So the connection is via this Pongarello-Long equations. Okay. So what is the Pongarello-Long equations, right? So Pongarello-Long equations is just I give you a real declosed 1-1 form on the whole space, and I want to find the potential of it. If you own compact manifold, you can always solve that. But this is we put it in the non-compact cases. Apparently, this is overdetermined because you're only looking for one unknown functions, but the equation is a lot. Okay, there's lots of equations. Secondly, this equation has huge kernels. So in PDE, the general philosophy is if you have a uniqueness, you have existence to some degree. Because you need to know, first of all, which category of the solutions you're looking for. And if you can have a good way to prove the uniqueness, usually that provides a way to establish the estimates to prove the existence. So this problem has a little bit tricky part is just the kernel is too big. So what are the kernels? You throw in any real part of holomorphic functions, it doesn't change anything. So if you add any real part of holomorphic functions, it always satisfies the same equation. So there's a huge kernel. Okay. But the Chen and Yao proved this Liouville theorems about harmonic functions. Remember that? That proves any sublinear growth harmonic functions must be a constant. So that kind of gives you a way to locate a good solution. Namely, you stay in the smaller class. So you look for the solutions with sublinear growth. Then two of them differs only by constant. Because if you look at two solutions, U1 and U2, the difference satisfies dd bar of the difference equals to 0, which is particularly harmonic. So then you're in good class. Then you have a hope to have existence schemes. Okay. So I try to explain to you quickly what is the technical issues. So the method was on manifold setting. Of course, this equation was proposed by Poincaré and Liouville. They must study this in their understandings of complex variables. But on manifold setting, probably Mock and Su and Yao is the one who studied it first. So they already adapted this method. Okay, this method is, instead of solve the overdetermined system, I solve a Poisson equation. Okay, so any solution satisfies that. If I trace it, I get Laplace U equals the trace of rho. So F being the trace of the rho. So it has to satisfy the Poisson equations. This is the strategy is, how about I just reverse the process? I solve the Poisson equations, and with good luck, the solution also solves the Poincaré rho. Okay, so that's a strategy. But that's kind of wishful thinking, right? It works sometimes. You need good estimate. So the good estimate is there's observations. The observations was due to probably Bishop and Goldberg. So they observed the norm of the difference is always subharmonic function. So if you can, for subharmonic functions, if you can prove at infinity that goes to 0, you're done. You can use maximum principles to conclude that it equals to 0 everywhere. So you need some good estimate on the you need some good estimate on this. So the problem is, from an analytical point of view, the problem is when you try to prove the estimate, we want to solve the Poincaré rho only knowing information on rho. Okay, so you could throw in conditions on rho like the L1 behaviors of rho. You have no idea about any higher power of rho. So the technical issues is this lack of good estimates, right? So if you do elliptic PDE, you know this there's LP estimates for Poisson equations. So, but the estimate only established estimate for P bigger than 1. At P equals 1 is only weakly 1. So even that was proved by Kaiser and Zygmunt using this crazy decompositions of cubes. So you couldn't do that on a curved space. So that's really the issues we have to overcome. So there's no good way to get hashing estimates of the solutions, assuming only the L1 conditions on the right-hand side. So that's really the techniques. And we worked quite hard on it. And Tang and I proved the result with additional assumption like this, which is not really natural.
But is that function log convex or concave?
Which function?
In the brackets.
No.
Ah.
No. This is any given 1-1 form. I take normal. There's no holomorphicities involved. So, well, I shouldn't say it's any given. I mean, in the application cases, the rho is a rich form. We try to apply. Okay. So I should explain the relevance first. So the relevance is, we try to solve this equation. For instance, for the right-hand side being rich form. So if I know informations, if I know the scalar curvatures has some good decays, I know the rich also has certain good behaviors if I assume non-activities, right? So the key is if I can solve this, if has a solution Ux, and this solution is automatically Plurisubharmonic because the dd bar of it equals to Ricci, which I assume is non-negative. Okay, so which is Plurisubharmonic. And this is the estimate part. Okay, you can prove some estimate. For instance, if you can prove this is some little o of log Ix, so then you're in business, right? Because we can use the Liouville theorems to conclude U is constant. Then I get the flatness of the manifold. So that's the relevance. So of course we have to establish the estimates. The estimates is kind of it's kind of natural because so elliptic PDEs, you have some sort of improvement by degree 2. So if you have the second derivatives is like r minus 2, then the solutions has some growth of log. It's kind of improved by 2. That's why you have this kind of estimate. Okay. So as I explained, the main issue is on the hashing estimates. So I try to say here we have to use the parabolic techniques to circumvent this technical issues. We have lack of a good L1 estimate for the solutions. So it's kind of mysterious. I have not completely understand why we have to do this. And certainly the Keller condition is very important. We use the Keller identities quite heavily and crucial in the argument. Okay. So I have encountered this in several occasions. So for instance, in early work, I did some dimension estimates on the holomorphic functions of polynomial growth. I applied these principles of comparing the behaviors at infinity with the behaviors at the spatial behaviors at one point. So this is basically you have a solution to the heat equations. So you use the asymptotic as the infinity to control the behaviors at for the initial data. And the key, we do not have like Birkhoff's theorems assert certain equations. The key is inequalities. Here the inequality is supplied by the monotonicity. So there's some monotonicity principles comes in and it allows you to do the comparison. So I would say this has been around by people, right? Has been around in the study of parabolic PDEs. For instance, Richard Hamilton once gave a talk. His title is The Beatles and the Rolling Stone. So Beatles, he means the dynamics of insects. There's a prey and the predators, right? So there's a dynamics reaction equation. And the Rolling Stone he meant is the Gauss curvature flow, how the stone was eventually evolves on the beach. So he has been quite successful in this regards, right? So what he does is he tries to understand how the ODE system works, then to apply that to the PD. Okay, so in a kind of rough way, in the sense to establish estimates in the form suggested by the not suggested, I mean given by the ODE. So here, what I'm trying to say is a slightly different thing. What I try to say, this is a connection between asymptotics. So you really have to know the asymptotics of the solutions. And then you use the asymptotic of the solutions to infer informations of your initial data. So it's a little bit different principles from what Richard has been doing. I mean, this is like a guiding the method in the study of the Richard flow. He uses quite a bit. Try to understand how the curvature equations evolves under the flow and try to prove for the PD. Okay. So there's also another cases had a success is the gap theorems I mentioned, I proved in 2012. So in these cases, I used a method to deform a 1-1 form. You try to understand the behaviors of differential forms, then use that to infer the informations of the initial metrics. So again, in that case, is also a monotonicity is a key. Okay, okay, this is a little bit technical now. So let's cut it out. Sorry for that. So let's don't worry about the lower bound. It's really only the upper bound that matters. So for application, only upper bound matters. So we only want to know it grows not too fast. Okay, this result is basically asserting about solvabilities of Poincaré-Laurent equations. Okay, so it applied to the cases we can use to solve this, to do this gap theorems, because the assumptions on the scalar curvatures guarantees this assumption. Basically, it says the average. Okay, I didn't explain what's K, right? So Kr of any function f is defined to be the average of my function f on a ball of radius r for some fixed O. So that's the definition. So if the average is L1, okay, if you are quadratic decay, because this is non-negative, so the trace and its norm is same thing. The average is L1 because it's quadratic decay. I mean, I shouldn't go from 0 to goes from 1. So really, the behavior matters is at infinity because it's smooth manifold, finite. Okay, then you can solve the Poincaré-Laurent equations, and with the estimate. So this estimate just anchors the kind of a unique good solutions. So without that, you don't know. I mean, you have lots of wide solutions. Okay. So that's the theorem. So we can prove. And the proof itself also uses parabolic method. Okay. So this is not a good theorem. Okay. In the sense, this theorem is a mechanism, kind of like a black box. You fit in something, you have something come out. Okay. So this theorem the statement is quite long. I'm going to explain that, then I'm done with it. So this is the same philosophy. You have to go through the whole parabolic process to produce good solutions for elliptic equations. So the theorem has lots of assumptions. The conclusion is very short, just one line. But the assumptions is very long. Okay. So A is just part of the assumptions. Okay. So what it says? It says if you can have a solution to the Hodge-Laplace heat equations of a differential form, a 1-1 form, okay, with the initial condition, 1-1 form, and your solution satisfies this estimate. Okay. Moreover, also satisfies this estimate. That's what is the assumption is. Assumption says you have a solution, and you have this kind of the space-time average decay estimates in terms of LP, and also you have this point-wise decay estimates. Okay. The very important assumption is this solution has to be closed. In applications, that turns out to be most difficult things to prove. The other ones are relatively easy. Second part of assumptions. Okay. So I'm sorry, the conclusion is just one line. The second part of the assumptions is you also can solve the scalar heat equations with the initial data being the solutions to your Poisson, because we already know how to solve Poisson long ago. So if you can do that, and this solutions also satisfies this decay estimates in terms of average space-time and point-wise estimates, then you have a solution to Poincare law. But this proof is not completely trivial. Okay? Despite the theorem does not look nice because the assumption is 2 pages and the conclusion is 1 line. But the proof, essentially, you have to use Keller identities heavily. It's not completely trivial.
With the assumptions you have counterexample.
I don't know. So this is
Whether you know or not.
I don't know. What I try to say is this theorem is really provide a tool for you to solve the Poincare law equations via a parabolic passage. Okay. You may have other ways to do it, or you may can improve conditions here and there. It's possible. But this is just to provide one passage. It's not unique. So in the applications, the assumptions all can be verified. You can prove. I mean, this is relatively easy to prove. This essentially was known to Li and Tang many years ago when they studied harmonic maps. They already studied this kind of scalar equations. So all contributions really on the A part to establish the conditions for A. We can construct 1-1 form solves the Hodge-Laplace equations, and that satisfies all the assumptions we need. That's why we can solve these problems. So the main thing I want to convey is parabolic method sometimes has a little bit of advantage, and it sometimes can solve in special circumstances like this on Keller manifolds. It can solve the problems the elliptic method does not deliver. Thank you very much.
That's a plug for parabolicity. Are there any more questions?
So can I ask just philosophically? You say that you don't use Virchow theorem, but it is analogous to it. That's what you said? A couple slides back, you mentioned Virchow-ergodic theorem.
Yes.
So
no, I'm not using it.
But so what you do is similar.
What I did is an analogy. So I try to use a large term asymptotics of a parabolic solutions to a parabolic equation or systems to understand the spatial properties of the initial data.
So in other words, you refer to what we call sometimes the body principle, that the time average equals space average.
Right.
But the Virchow theorem is only one of versions of it and pretty delicate and not always working because it's pointwise theorem. So is it still fair to say that maybe what you are doing is similar also to von Neumann, which is convergence in norm and which is in some senses much more general than Virchow?
Well, we do. I mean, in terms of estimates, we do need both the pointwise at a large time and the pointwise of the spatial. I mean, not every cases, but many of them we need the pointwise information.
At some point you mentioned the lack of Calderon-Riemann types. So when you say the lack, you mean that it's not true, or we don't know whether it's true, or we just don't know how to formulate it properly in this setting?
Okay, so there's 2 separate issues. For one, we don't know how to prove it. To prove even weakly, the weakly L11 estimates for solutions to the Poisson equations on a curved space. Secondly, that is not enough. because we need a strong L1 estimate.
Okay, well, let's thank our speaker again.